Okay, we've looked at information theory from the point of view of coding aspects. I'm going to finish off the overview of information theory with something that may seem a little bit odd, a little bit strange. And this is a topic of predictive text and a model of predictive text and language called n-grams. What are you going to say? Confusion is a word we have invented for an order which is not understood. It is the order of an accidental series of accidents, accidentally conceived. So this is by the great American writer Henry Miller in his novel Tropic of Capricorn. Let's go on to the main topic. So we saw, looking at character coding and Shannon's ideas about source encoding, channel encoding, that information is concerned with notions of uncertainty, not knowing what to expect, and surprise, seeing the unexpected. So Shannon's discovery that information content can be interpreted as a progressive reduction in a level of uncertainty. This has some quite significant consequences that are still of importance today. So part of Shannon's researches led him to investigate a notion of entropy and redundancy in spoken language, not simply sequences of symbols. So we'd seen that character coding can allow us to compress the amount of data sent, and that this is based on an analysis of the frequency of individual characters in a stream of text. What happens when we move from individual characters to words? Now, we saw that character streams can have an element of predictability. For example, the letter Q is usually followed by the letter U. The symbol for space rarely followed by the letter X. And although those are features specifically of written English, we can find similar patterns in other what are referred to as Indo-European languages. In fact, although the notion of written text is very different, we can find similar patterns in languages such as variants of Chinese, in Japanese, in Arabic, in Sanskrit, and so on. So that's characters. What about words? So here's a very basic example. Let's take the part sentence, the cat sat on the. What word does one think most people would use to complete that sentence, to replace the three dots? Suppose we have a choice of hat, rug, couch, sofa, mat, rat, ottoman, chaise longue. One would expect the typical choice would be mat. The cat sat on the mat. Why is that the case? Why would most people choose mat to complete that sentence? Is it because it rhymes? But in that case, one might expect a significant number to choose hat or rat. Is it because of the sense? One sits on something, but then one would expect a significant number to choose rug, or couch, or sofa, or ottoman, or even chaise longue. The reason why a significant number would choose the word mat is familiarity. So the small sentence, the cat sat on the mat, is standard children's reading exercise. Now, in a child's reading exercise, you would be unlikely to encounter obscure terms like ottoman or chaise longue. So, we have other examples of this type of behavior. There is the annoying habit of finishing another person's sentence before they are finished speaking. One has a behavior in editors such as MS Word with suggested continuations of the text being typed are given. Similar thing in Google, suggested search terms based on what has been typed so far. One has speech recognition systems, particularly as used to provide transcriptions of text for automatic subtitling, automatic captioning. Now, there are some significant differences between those 5 cases. If we take the finishing somebody's sentence for them and the cat sat on the mat example, one feature of the accurate prediction is it tends to be based on a sort of shared cultural, sociological background. It is not something that is based on statistical analysis. The cat sat on the mat. This will be a phrase recognized by most adults over a certain age because it will be a phrase that is familiar from childhood. Ending a speaker's sentence for them, again, that is presuming a similar awareness of the speaker's topic and the speaker's background. If we look at the predictive text examples in editors and in search, these are less driven by common cultural awareness. Although this does feed in, Word is going to be used by people, a whole wide range of backgrounds. Google search is similarly going to be used people with a very wide different range of backgrounds. So the predictive nature there is rather more based on statistical analysis of features, not on so much on shared cultural values. So the attitude there is the cat sits on a mat because statistical analysis would suggest that most cats have been reported as such. What about automatic captioning? So I think it was 2020, 2019 possibly, it became a legal requirement in the UK for all newly recorded and pre-recorded lectures provided to students to have subtitles and closed captions provided. Now, most video hosts, things such as YouTube, things such as MS Streams, do offer a feature to extract written text and captions from spoken content. You upload the video to MS Streams or to YouTube, and one thing that will be done is a transcript, the caption file will be produced. The quality of those captions is extremely variable, and it is almost always the case that some sort of manual editing, some sort of correction of the caption file is needed. If you talk to my colleagues who went through this process, did myself going through it, and one thing they will tell you is this is very, very tedious, tiresome, time-consuming, labor-intensive. Well, the legal requirement is to provide captions, no requirement to provide accurate captions. So, given that this is such a tedious and labor-intensive process, and you have a caption file available, why not just leave it as it is? Why bother with corrections? So, here are some examples from lectures that I recorded as to what was offered for transcribed captions. It seems that every exam has an individual weighter. The next part of the module will look at Foster rivets. We will also consider advanced matrix operations. And my favorite, the lecture will be in the most bad lecture theatre. So those are real examples. Now, it's not necessarily the case that these are always down to the speaker's accent, the speaker's vocal cadences, the speaker's inflections. That may influence the transcription, but it's not always the case. So, what was actually said with those 4 examples? Every exam has an invigilator, not an individual weighter. The next part of the module looked at using first derivatives, not Foster rivets. We considered using advanced matrix operations, not matrix operations. And finally, the lecture will be in the Muspratt lecture theatre. Not the most bad lecture theatre. Well, arguably not the most bad lecture theatre. So, we are looking at going from Shannon's work with character streams to using similar techniques but dealing with words. And we have a difficulty. It's fairly straightforward to conduct extremely accurate statistical data about how frequently individual characters, individual symbols occur. We can take comparatively small text example, a chapter in a book, an article in a newspaper, a short story, and derive that information. There is In fact, an experimental claim called Zipf's law, this has been validated by a number of research studies, and that claim asserts that the kth most commonly used character in a language occurs roughly 1 over k times as often in text as the most frequently used character. So we can build a graph such as this one. The most frequently used character, the letter E, occurs significantly more often than the least frequently used characters, J, X, Q, and Z. But what about words? Well, it is possible to carry out a similar analysis, but it is much more demanding. If we develop that idea further, then one thing that comes out as a result is a very important idea called n-gram language models. I'll say a little bit about those. I'm not going to discuss those models in depth, but I will introduce the basic elements of those. It's also the case that Zipf's law, which I mentioned with respect to language, to alphabet characters, also has been observed to hold for words. The most frequently used word in a text compared to the kth most frequently used word. The kth most frequently used word occurs roughly 1 over k times as often as the most frequently used words. Okay, so what exactly is a word? We have an understanding of what we mean by an alphabetic character. What do we mean by a word? Well, again, if we look at Indo-European languages, things such as English, French, German, Italian, Spanish, the one way we can say what is meant by a word is it's a sequence of characters using the language alphabet that is accepted by some authority. So, for example, a standard dictionary. In English, we have the Oxford English Dictionary. In US English, we have Webster's. In French, we have Larousse. Liddell Scott is one of the standard lexicons for classical Greek. DRE is the dictionary, or the authoritative dictionary of Spanish words from the Spanish Royal Academy. DWB is the Deutsche Wörterbuch, which is one of the authoritative sources for German. That was started by the Brothers Grimm in the late 18th century and finished in the late years of the 20th century. So we have standard dictionaries which allow us to say this is a word in a given language. So those provide the basic units we can use to look at frequency, but in order to analyze frequency in itself, we need what is referred to as a text corpus. So we analyze letter frequencies using single articles in words. What we mean by a text corpus is basically a massive body of writing works in that particular language. And that gives us the basis to understand how frequently individual words occur. So I mentioned n-grams. What are n-grams? So the idea behind an n-gram is to look at the relative frequencies of sequences of words, and these are used to guide prediction, to guide interpretation, analysis of style. They have even been used as a means of creative writing by a computer program. Some very common choices of these are what are called bigrams, n equals 2, trigrams, n equals 3. And all they are, an n-gram is just a sequence of n words. Notice it has to be a sequence. We are not talking about a set of n words. We're talking about a sequence of n words from the language. So we have some text corpus, some collection of writing. And to this we add start and end sentence markers. And the relative frequency of a given n-gram, well, that's defined by this rather frightening looking object there. What does that mean? That says that the probability that we will see the sequence of n words in a text is the probability that the first n minus words are seen and followed by the nth word relative to the total number of times we see that sequence of n minus 1 words in the text. Let's look at a very small example. So suppose we're looking at bigrams, n equals 2. Let's take a set of 4 sentences. In the beginning was the Word, and the Word was with God, and the Word was God. The same was in the beginning with God. All things were made by him, and without him was made nothing that was made. In him was life, and the life was the light of men. So we got 4 sentences. This is, of course, the opening of Gospel according to St. John, the first 4 verses of that. I've used the Douay-Rheims translation as the source. And we have, you will see, start sentence tokens and end sentence tokens. And the reason why those are introduced is if we have those introduced surrounding individual sentences, then we do not need to vary the model to take into account different sentence lengths. So what do we get from that example? So these are all bigrams in that example. Sometimes the word the is followed by the word word. Some sentences start with the word in. Some sentences end with the word God. The word was is followed by the word made. The word the is also followed by the word beginning. Now we look at our counts for those. There are 3 occurrences of the bigram the word. There are 2 occurrences of the bigram the beginning. There are 2 sentences that end with the word God. There is a single sentence that starts with the word all. If we look at what are called unigrams, single words, there are 7 occurrences of the word the. There are 3 occurrences of the word God. So if we look at our relative frequencies, that tells us that the probability that the word the is going to be followed by the word word, that is 3, the number of occurrences of the bigram, the word, divided by 7, the total number of occurrences of the word the. The probability that a sentence ends with the word God, the probability of the bigram end sentence God, that's a half, because there are 2 sentences that end with the word God, and there are 4 sentences in total. The probability that the word the is going to be followed by the word beginning, that's 2 out of 7, because there are 7 occurrences of the word the, and on 2 occasions that is followed by the word beginning. The probability that a sentence starts with the word all, that's a quarter. Exactly one of the sentences starts with the word all. So that's a very small example, but we can apply exactly the same analysis to much larger texts, complete works of a single author, complete novels. So how do we use n-grams? Well, let's focus on bigrams, for example, or sequences of pairs of words in a text. So the first thing we have to do is to construct all bigrams and compute the relative frequencies using the formula that I gave earlier. Suppose we want to use that as an assistance in predictive text. And one thing we can do when it is recognized that a given word W has been typed, we may suggest as a continuation a word X where the bigram WX is the one that occurs most frequently of all the bigrams that start with the word W. Now, we probably want to use a threshold there, so we may decide only to offer a continuation if the bigram WX occurs with relative frequency at least 0.9 or 0.95. In creative writing, if we've carried out a bigram analysis of a given corpus of an author's written work, we may use that to analyze random selections of words in order to parody the writing style of that author. In a topic called stylometry, one thing we can do, or we can use bigram analysis to feed into, is informing a writing profile of that author. In plagiarism detection systems, we can use bigram or n-gram analysis of characters rather than words to look at large items of writing, for example, something like a project dissertation, and see if there is a significant variation in profile over chunks of text from that dissertation. So, for example, we may analyze sections of 1,000, 2,000 characters at a time, moving a window of text over the whole work, and then seeing how n-gram profile varies over different windows. And that may provide evidence that multiple authors have contributed, and so provide evidence that the dissertation is not the work of a single author, but of several authors, and perhaps suggest plagiarism or collusion has occurred. So in summary, Natural language analysis is one of the major areas, major applications that arises within data science. And the methodology given by Ngrams that has developed quite considerably, so it's now quite sophisticated. I've only given the flavor of the basic techniques. Ngram packages and natural language tools are actually provided within Python itself. So one of the Python methods available within the public domain is something called the Natural Language Toolkit. Stylometric analysis has also been used to uncover fraudulent practices and has been considered as a tool to deal with generative AI abuse.